Hi students, welcome to our channel Physics Concepts by Ali sir. In today's session, now let's discuss about simple harmonic motion. So first of all, oscillatory motion. A oscillatory simple harmonic motion is a special case of oscillatory motion. Oscillatory motion. If any one particle from the main position, if it is making a to and fro motion, the particle is said to be in the oscillatory motion. For example, now let us take any one spring. The spring is connected to any one mass m. So here now once this is we are calling as the at present the block is in the rest position. At this position we used to call it as main position. So generally main position now it represents with the letter of O. When we applying force, this spring will extend till here, and this is reaching to the maximum displacement, from where maximum how much distance it can stretch, that's we are calling as amplitude. So here is this amplitude, and again due to the object won't be stays there due to the restoring force, means that force makes the object to move back. So because of that restoring force, again the particle starts moving towards this side, and so again what will happen, this particle will come. For example, if you suppose to draw again, now the particle will come, or the mass of the object will come till here, and here what is happening from this main position, here is actually the block, but it is just moving towards this side as well as later on this time, and it is coming towards this side. So the particle, now we can take the one more way of this illustration. Now let's assume that this is the particle. The particle is traveling towards this side, and because of the restoring force, the particle will come. It won't stop here. Again, it will travel some more distance. This is one extreme position towards the right side. This let's consider as a positive. And again from the main position, this is the main position, means where the object is starting. From the main position, the particle is traveling towards extreme position, and afterwards due to the restoring force, the particle will come towards this side. This is also we can call it as extreme position. This extreme position now let's consider as a negative. And here the particle from the main position, it is making to and fro motion. That type of particles motion is called as a oscillatory motion. Means the particle has to move in the towards from the main position, it has to move that in the to and fro motion. The object is said to be in the oscillatory motion. Then here why the particle is coming again back, due to one force. So that force, now let us take that force F, that is directly proportional to minus x power n. Then that we can consider as F is equal to minus a k into x power n, whereas x is the constant and x is the displacement of the particle, and so n is the number of particles, how many times it is just moving. And here this F is equal, if you observe the negative sign, the negative sign shows that the applied force and displacement and both are in the opposite direction. So the motion of the particle is in the opposite direction of the main position or applied force. That is we are calling as oscillatory motion. And SHM is simple harmonic motion. It is a special case of oscillatory motion. Then what is meant by simple harmonic motion? And so before that, now let us take a few things about that one. When in a particle is considered as a simple harmonic motion, generally a wrong conception is the particles are, if they are in the circular motion also can be considered as simple harmonic motion. No, the particle simple harmonic motion, the particles starts traveling in a straight line motion. So the particles in the SHM, they used to travel in a straight line motion. Next here is the first one is, what are the, when can we say the particle is in the simple harmonic motion, or what are the conditions has to be satisfied by the particle to be in the simple harmonic motion? First one, that should travel in a straight line. So the motion of the particle must be in the straight line. Next, that should travel in a to and fro motion, straight line, as well it should make to and fro motion, and the particle once when we applied force, it changes towards this direction, it's moving some displacement and it has some velocity, and that velocity leads to an acceleration. That acceleration must be directly proportional to the x, means that acceleration is directly proportional to the displacement, and apart from that one, that has to be the displacement must be, the acceleration must be the opposite side of the displacement. For example, the particle is just making the displacement towards the right side, but acceleration should react towards the magnitude of the amplitude, but it is opposite to the direction of the motion of the particle. Means, for example, the particle is moving this side, so the acceleration should act opposite this one. For example, a particle is moving right side, the particle has to acceleration, the particle should be the right side. Next one, all the time this arrow mark shows you that the direction of the acceleration is opposite to the direction of the displacement of the particle. Next also we can consider, then again here is this acceleration, all the time it has to act towards mean position. So these all are the conditions for a simple harmonic motion. So then what definition we can drag from this one? So then when a object or a particle is said to be in the uniform motion, the particle is said to be in the uniform motion if that particle is traveling in a straight line, making a to and fro motion, that acceleration is acting towards the displacement, and the direction of the acceleration is opposite to the direction of the particle displacement, and the direction is all the time it has to travel towards mean position. Then once when it is following these all factors, the object is said to be in the simple harmonic motion. And so simple harmonic motion, the types of simple harmonic motion, basically two types we can take, and that is one is linear simple harmonic motion, next one is angular simple harmonic motion. So then what is example for linear simple harmonic motion? Now let us take any one spring, and once we are taking the spring and we are applying a force, so the particle will move in the linear direction. Then we can say this is an example for the linear SHM, that is a spring and mass. The second one we can take, if we suppose to take any one U-tube or U-shaped tube. In this one, if we take the liquid, the position, the movement of the liquid is moving up and down. So that is also an example for a linear simple harmonic motion. Angular harmonic motion, then we can take simple pendulum is there, or any one clock. In the clock pendulum is there, the motion of the clock also we can consider this is a simple harmonic motion. And one more example we can take. Now if we suppose take a hemisphere ball, in that one, now let us take any one ball. The ball is making when we are dropping the object, the ball will go upwards, as well as again it comes down. Excuse me. So the particle is going towards this side, and so the particle is moving to and fro, that we can call it as a angular simple harmonic motion. So this simple harmonic motion can be explained by means of then one circle we can take, reference circle or phasor diagram also we can take. Through reference circle, now let us discuss about the simple harmonic motion. So then what is meant by a reference circle? So reference circle means, now let us consider what is meant by a reference circle. Through reference circle we can explain the simple harmonic motion. So reference circle in sense, a projection of a particle, on projection of particle performing uniform circular motion on the radius of the circle is mathematically called as simple harmonic motion. Projection of a particle. So, projection of a particle, if we suppose take any one particle, that particle is just projecting on any one uniform circular motion based on the radius, then we can consider that is called as a simple harmonic motion. Now let us take the illustration so you will understand. Now let us take first of all any one circle. In this circle, now let us take the x-axis and y-axis. Now let us consider this is a x dash and y dash. Assume that this is one circle. Assume that one particle is making a project moving with uniform velocity. So it is just moving at here. It is traveling towards this side with a uniform velocity. So it is making some certain angle theta. This theta value we can consider as, so that is equal to omega t. So how this omega t? Omega is angular velocity and it is a angular velocity in sense angular displacement by time. So omega is equal to angular displacement is a theta and the time is a t, and so then theta, that is equal to how much is that? Omega t. So that theta is equal to omega t. So it is making certain angle with this one, and right from here you draw one perpendicular on a y dash. So this is, let's consider as this is a p. This p is called it as a projection. So here it is making omega t angle. Naturally here also it makes a omega t angle here. Now the radius of this circle is a, let's assume, and the projectile distance, now let's call it as a y or a x. So we can take y as well as a x also we can take, no problem in that. Now let's discuss about how the projection takes place. Along with that one, how the circle is going on. So the first situation now let us take, and situation 1. So the particle is traveling from x dash to y. So x dash to y. So then where the projection is? The projection is starting from O to y. The projection is O to y. And again now the particle is starting from y to x. So in the second situation, y to x. The projection is, from where the projection will start? The projection will start from y to o. The particle starts from x to y dash. So that is x to y dash. So x to y dash, the particle, then the projection will start from o to y dash. Next the particle is starting from y dash to x, y dash to x. The particle y dash to x, in sense the particle starts from y dash to o. So y dash to o. Then what is that? If you suppose to observe, the particle is starting from o and making a certain displacement and makes again it the original position. So this example shows that SHM simple harmonic motion is nothing but projection of a particle on uniform circular motion, a projectile projection of a particle making or performing the uniform circular motion based on the radius. This is we are calling as simple harmonic motion. Now let us see the properties of a simple harmonic motion. So what are the properties of the simple harmonic motion? The first one, now let us take the displacement. So what is meant by displacement? Now let us take. So displacement means that is the displacement, the total path covered by particle in SHM from its mean position. So for example, now if we suppose take this particle is any mean position and this particle is traveled till here. Now let us assume that is y. So this distance, total distance, how much it is traveled is called it as a displacement. Distance travelled by a particle in the SHM from its main position is called as a displacement. So for this displacement, now let us discuss the value for this one. For this one, now let us consider this triangle. Assume that this is now let us call it as A. From this O triangle OP A, now if we suppose take sin omega t is equal to how much is that? So that is opposite and A. So y by A, ultimately then y is equal to A sin omega t. It's very popular displacement. This is what we are calling as the expression for a simple harmonic motion. Y is equal to A sin omega t. Sometimes instead of y we can take x also, there is a no matter. X also, this one also we can consider x is equal to A sin omega t. This one also we can consider one of the expression for the displacement. So after completing the displacement, now let us see the next one. So the next one is then we can take velocity. So velocity v is equal to, so what is the velocity in terms of the differentiation rate of change of displacement is called as a velocity. So we have to make the differentiation for the displacement y. Then we will get, so can you write this? So there is a sufficient place for this. So here is, now let us take this. So here is, now let's make the displacement here. So y is equal to v is equal to dy by dt, differentiation of velocity. So then that is equal to d by dt of A sin omega t. So here is equal to A is a constant, d by dt of sin omega t is cos omega t. Again differentiation of omega t, chain rule. So we are using chain rule for differentiation. So then A cos omega t, again d by dt of omega t in sense of omega, ultimately we can write A omega cos omega t. This is one of the very popular expression for a velocity. Velocity of a particle in the SHM is P is equal to A omega cos omega t. So now let's keep one more expression. Now let's write for this one. So sin square omega t plus cos square omega t is equal to 1. From this one, now let us take cos square omega t is equal to 1 minus sin square omega t. So here is then sin omega t. What is the expression we have for sin omega t? Sin omega t is equal to y by a. So from that one, then what we can consider? Then cos square omega t is equal to 1 minus y square by a square. Cos square omega t is equal to, now let us do the LCM. So you will get a square minus y square by a square. So ultimately then what you will get? Cos square omega t. So then here is then v is equal to, we can consider cos square omega t. Now we need only cos omega t, because cos omega t should be substituted in this one. Then square root of a square minus y square by a, because square root of a square is equal to a. Now from this one, v is equal to a omega cos omega t in sense a square root of a square minus y square by a. So a get cancelled, that is equal to omega into a square minus y square. So this is very popular one, v is equal to omega. So one more expression I will write here. Then omega v is equal to omega square root of a square minus y square. This one y can be considered in x also, depending upon the situation. Means y x similar terms we can take, that counts for a displacement only. So here is v is equal to omega square root of a square minus y square. Now let's discuss still about this omega, these are things. So I will wipe here, see. Now here, now let us see, let's discuss more about this velocity, because this will come in exam. Now here v is equal to, we have omega a square minus y square. Now let us take one particle is there, this is at the mean position. So at mean position displacement is 0, because the particle is not moving. Once the particle is moving towards right side, then we can call it as extreme position. At extreme position, it has a maximum amplitude. So x is equal to a. Maximum displacement is called as a amplitude. So x is equal to a, and of course, even it is traveling from this side, this side also amplitude, but that is minus a. Okay. Now here is, now let's discuss where the velocity is maximum in the SHM. So for example, now let us take first mean position. When we are taking about the mean position, then how much is x? X is equal to 0. Then v is equal to omega, velocity how much is that? Square root of a square minus 0 square. So x and y both relevant terms, we can use that, and so that is equal to omega a. So the velocity is the maximum where it is in the extreme position. At extreme position, the velocity of the SHM is maximum. What about at the mean position? So we have taken velocity is at mean position, not extreme position, mean position, at a mean position. So the velocity is maximum at a mean position. So then what about the extreme position? Sorry for that, extreme position. So now let us take the extreme position. What is at extreme position? At extreme position, x is equal to maximum displacement, that is amplitude. So x is equal to a. Now let us apply this one. V is equal to omega square root of a square minus a square. So that is equal to how much is that? That is 0. So V minimum, where it is at extreme position. So here is V is minimum, and here is V is maximum. So this one also we have to keep in mind. That's all about velocity. Now let's discuss about the acceleration. So then here is now let us take acceleration. How that acceleration is changing. Now let us go that. So then what is meant by acceleration definition? Rate of change of velocity, or differentiation of velocity gives us a acceleration. So here is now acceleration a is equal to d by dt of 1, the velocity we can take. So then this is equal to v. So d by dt of a omega cos omega t we have. Now let us take the differentiation. Let us apply. A omega is a constant. So next d by dt of cos omega t, that is equal to a omega d by dt of cos omega t minus sin omega t into d by dt of omega t. So that is equal to a omega into, now let us write minus a omega sin omega t into omega. Then ultimately how much? Minus a omega square sin omega t. This is the formula for the acceleration. So acceleration formula a is equal to minus a omega square sin omega t. But here what is the displacement or displacement definition? Distance displacement a sin omega t. So this can be reframed. Acceleration can be reframed minus omega square a sin omega t. So instead of a sin omega t, we can write y. So a is equal to minus omega square y. This is an expression for the acceleration. So here is now how this will be changed. Then this can be changed in the main position. How it will be changes? Now let us see. The same example, now let us take here how it is changing. At extreme position, mean position x is equal to 0. So mean position Then what is the acceleration? A is equal to minus omega square into 0. So 0 means at a mean position acceleration is a 0, but in the mean position velocity is a maximum. So see that one. At a mean position the velocity is a maximum, but acceleration is 0. Then what about the at extreme position? At extreme position, so minus omega square a, that is acceleration is maximum. But when these both are opposite, in extreme position acceleration how much? 0. But extreme position acceleration velocity is a maximum. In this way, just then we can take about the how these all simple harmonic motion and their properties. I hope that this session is helpful for you. Please support me, Nana. Wish you all the best.